So in this video, we're going to continue on with the algebraic solution to determining absolute extrema and local extrema. By now, you should have actually attempted the Desmos activity, which addresses these two concepts. So when looking for turning points, which is a kind of a local extrema, local max, or local min, we're going to have to look for where the slope is 0. So in other words, we want the derivative of the function to equal to 0. Now we're going to have to talk a bit about two new terms, critical numbers and critical points. So critical numbers is the x value for where the slope is 0 or undefined. For the undefined part, I'm going to readdress this later. It really depends on the function. And a critical number is the x value. The critical point is both the x value and the y value, because sometimes the critical number may not be part of the domain of a specific function, and we'll get to that later on. The last thing is, well, what does a function that has an undefined slope look like? So if you recall in the past, a function where the slope is undefined means it's a vertical like tangent. So basically imagine you're having a, I think we talked a bit about cusps, so cusps is one of them, so something that's really pointy. So over here we have a vertical tangent, or sometimes we might have a inflection point, but over here the slope is very vertical. And the slope is vertical, we know that the rise is going to be something, a number, but the run is going to be 0, and therefore it is undefined. So that's one of the examples where a slope is undefined. And in future lessons, I'm going to show you other features of a graph where the slope is considered undefined. So just a recap of derivatives. So if you recall the first principles, this whole thing is first principles, this is the derivative. So when the derivative over here, when f prime is greater than 0, that means that the slope is positive. And when the slope is positive, we know that the graph is going to go up. The question is how it goes up. It could go up straight, it could go up like this, or it could go up sort of like a square rootish. So there's a couple of ways that a graph can increase when the slope is positive. For this one here, when the slope is negative, or the derivative is less than 0, we know that the graph is going to go down somehow. It could go down like this way, or it can go down like this way, or it can go down like this way. There's a couple of ways, or it could be a combination of both. In the Desmos activity, we encountered a cubic function over here, and we know that over here, a cubic function could have two turning points in this particular example. And the question right now is, how do you find the x value for these two turning points? So we talked about finding the critical points, or where the slope is 0. So imagine this function is f, and you want to find the derivative of this function, and you want to set it to equal to 0, because over here, we know that the slope here is flat of the tangent, and therefore the slope is going to be 0. So in order to find the x value for the turning points, we're going to have to set the derivative equal to 0. Well, after you find these 2 points, you're going to have to classify them. So in terms of algebra, how would you show that this point over here is a local maximum? So one way we can do this is we can check the slope to the left and check the slope to the right. So for the left of this point, we know that the slope is positive, or f prime is positive, and over here to the right side of this point here, of the turning point, the derivative here, or the slope here, is going to be a negative. And vice versa, if we check this point over here, well, we know that just physically we can see that the turning point is a local minimum, but how are you going to prove that algebraically? Well, one way is we can actually go to the left of the function and figure out the slope to the left. And in this particular example here, the slope is going to be negative. And over here to the right, the slope or derivative is going to be also positive. So in other words, we're going to be setting up something we call a first derivative test by checking the slopes to the left and slopes to the right of the critical points. So here we have a cubic function, and we're going to figure out all the critical points and classify the types of local extrema and see if there is an absolute extrema, max or min, given a restricted. So now we have a cubic which is restricted between -1 and 3. So let's find the critical points first. So critical points means, all right, so let's figure out the derivative. So we're going to find the derivative using the power rule here, and we end up from a cubic to a quadratic. And this would be our derivative. If you want to find the critical numbers, remember critical numbers means you want to figure out the x values of when the slope is 0. So we're going to take the derivative, set it to 0, and in this particular case, we're going to have to factor, and we know that each of these factors contributes to the critical number. So in this case, we have 2 critical numbers. Now the question right now is, are these critical numbers points? Well, critical points means y value. So if you substitute x for 0 and x for 8/3 into the original function, well, you get a y value. And we know that cubic functions are, they're xer, yer. So we know that the y values will exist. So I'm just going to quickly substitute 0 into here, substitute 8/3 into here, and we end up getting 3, and we end up getting some sort of number, which is -6.5-ish, I think. All right, so the next thing we're going to do is we're going to classify them. So over here we have 2 points where we know that the slope is 0. But the question is it a turning point? And if so, well, how are you going to figure out whether it's a max or local min? And let me introduce you to the first derivative test. So first derivative test means you're going to use the first derivative. So to set this up, we're going to set up a interval chart. We're going to figure out all the critical numbers from lowest to highest. So over here, I'm going to write down x is equals to 0 is a critical number. X equals to 8/3 is a critical number. And we know that we're going to, right over here, we're going to put in the first derivative. So the first derivative is going to be 3x squared minus 8x. So that was our first derivative. And all you have to do is figure out a number that you can put in this interval. So let's find a number that's to the left of 0 and see what the slope is to the left. Let's put in x equals to -1 over here. When you put x into -1 into here, the first derivative, you're going to get a positive or negative number. And in our case, we're going to get a positive number. Over here, between here, choose a number between 0, x is 0 and 8/3. I'll choose 1. And if I substitute 1 into here, I'm going to get a negative number. And over here, I'm going to substitute, for example, 5 into the first derivative, and the slope is going to be a positive. So what that means is, in this little space here, I'm just going to draw the behavior of the graph. So positive means the graph goes up. Over here, the graph goes down. Positive here means the graph is going to go up. And we know over here, there's a reason why I put this dotted line here, is because we know that here the graph is going to be, the slope is going to be at that point flat, because these numbers give us, are the zeros of the derivative. And based on the way that the graph is curving, we know that over here, this point here, our critical number here, it goes up and then it goes down. We know this is a local maximum. And over here, if we look at this point here, to the left the slope is negative and to the right is positive. So we know that this graph is going to turn down to up, meaning it's going to be a local minimum. The last thing we're going to do is deal with the absolute extrema. So absolute extrema, absolute max or minimum, is the highest or the lowest y value. So in other words, we're going to have to determine the y values for our critical points as well as our endpoints, because these are the points at the extreme left and right. So over here, test the interval points. So let's substitute f at -1, f at 3, and we have f at 0. These are our turning points. F at 8/3. I know these ones we got already from before, -6.5. And all we have to do is substitute -1 into the actual y value and substitute 3 into the actual function. And then we can compare all the y values. So these two y values are from the endpoints, or the extreme, the left and the right boundaries. These two ones are from our critical points. And now you just have to compare which is the biggest one, largest y value. In our case, this here is going to be the largest y value. Therefore, I can say that this is also my absolute maximum. And the next thing you're going to do is find the extreme minimum. So between these three values, this one here is going to be the lowest y value, and we can say that this point here is the absolute minimum. So in our case, these 2 points can be classified as both the local maximum and an absolute maximum for this one here. And for this one here, this is a local min based on the first derivative test, but it is right now the absolute minimum. I want to actually have a look at a function, a polynomial, or where it is restricted. So here we have some sort of restriction, but the restrictions are open over here and closed over here. So let's go over local max and absolute extrema. So if I asked you what is the local max here, we can tell you what local max for a polynomial is over here. So over this point here, there is a local max, is a turning point. Over here, we have a local minimum. So the next thing is, what is the absolute highest y value here? So you want to look at the very top range of your graph, and based on this here is considered the absolute max, because this point here is lower than this point over here. Now, if this black dot here was, for example, raised up higher, so let's just say I changed this graph and had something over here. So now in this case here right now, the absolute max is no longer on this turning point, it is on the end point. So in this case, this would be the absolute maximum based on the change. So let's turn to absolute minimum here. So the absolute minimum is the lowest defined y value. So in our case, it seems like this area here is our absolute minimum area. However, you cannot say that this point here is a minimum of -5 because it is the open dot. Now, because it's an open dot, -5 is not part of the function. So in this case, we do not have a absolute minimum. Some students may argue, well, can't the minimum be -4.9999, something that's really close to -5? Well, if you say this, then someone can also sort of override you and actually add an extra 9s. So in other words, there is no absolute minimum. However, if it was closed, if I close this dot, then you can say, all right, the absolute minimum is a -5. However, if it was opened, then like this, then we do not have an absolute minimum. So keep in mind, absolute max and min must have a defined y value.